All right, welcome to the Explainer. Today, we're going to crack open a case that baffled scientists for centuries. What is the structure of the atom? It's a real detective story, full of invisible clues and brilliant deductions that completely changed how we see everything. You see, for the longest time, everyone thought the atom was the end of the line, the smallest, most basic piece of reality you could get. But, there were these nagging little mysteries, like the crackle of static electricity, that just hinted there was a secret world locked inside. And so scientists had to become detectives. They came up with these incredibly clever experiments to try and peek inside this hidden world. And what they found, well, it would change science forever. So, where does our story begin? Well, it starts back in the late 1800s with this piece of lab gear called a cathode ray tube. So, picture this, a glass tube with pretty much all the air sucked out of it. When scientists like William Crookes zapped it with a whopping 10,000 volts, bam, this mysterious greenish glow appeared. It was caused by these invisible rays shooting out from the negative end, the cathode. So, naturally, they called them cathode rays. Now, these weren't just some weird light beams. No, they were particles, and they had some very specific properties. The fact that they bent towards a positive plate, that told them they had a negative charge. They could actually spin a tiny paddle wheel, which is just wild, proving they had mass. But here's the real kicker. It didn't matter what gas or metal you used in the tube. These particles were universal, a fundamental piece of all matter. So this physicist, J.J. Thomson, he puts all these clues together, and he realized he discovered the very first subatomic particle, the electron. And just like that, for the very first time, we had proof that the atom was not the smallest thing out there. The case was officially blown wide open. Okay, but hold on. This discovery, it immediately creates a brand new puzzle, right? We all know atoms are electrically neutral. So if they have these negative little electrons in them, where is the positive charge to balance it all out? The hunt was on, and a physicist named Eugene Goldstein decided to find out. So this guy, Goldstein, he does something really clever. He takes the same cathode ray tube, but he modifies it by drilling these little holes, or canals, in the cathode. And when he did, he spotted brand new rays traveling in the opposite direction of the electrons. And what were these new rays? Well, they were the proton, the positive twin to the electron. With that, 2 of the 3 key players were on the board. The final piece of the puzzle, the neutral neutron, was way trickier to find. It actually took until 1932 for James Chadwick to finally pin it down. So here they are, the 3 key players in our atomic drama. But take a look at those mass numbers. The proton and neutron are almost 2,000 times heavier than the electron. I mean, that's not even a fair fight. It's like comparing a bowling ball to a tiny grain of sand. So the detectives had all the pieces, right? But now came the hard part. How the heck do they all fit together? Okay, so the first person to take a crack at drawing a map of the atom was the guy who discovered the electron, J.J. Thomson. And his idea? It got a pretty memorable name, the plum pudding model. Just imagine a blueberry muffin. The cakey part of the muffin, that's this big spread out cloud of positive charge. And the blueberries, those are the negative electrons just kind of dotted throughout. I mean, it makes sense, right? It was a really good first guess. But it was about to get absolutely demolished by one of the most legendary experiments in all of physics. Ernest Rutherford, who was actually one of Thomson's old students, decided he was going to test this whole pudding idea. His plan was to fire these tiny positive bullets, they're called alpha particles, at a super, super thin sheet of gold foil. I mean, this foil was practically see-through. And the thinking was they should just blast right through that soft pudding of the gold atoms, no problem. But what he saw was just mind-blowing. Yeah, sure, most of the particles sailed right through, just like he expected. But some got deflected at these crazy angles. And a tiny, tiny fraction, we're talking about 1 in 8,000, bounced almost straight back. As Rutherford himself famously said, it was unbelievable. 1 in 8,000. Now that might sound like a tiny number, but it was an absolute game changer. There was just no way a fluffy, spread-out pudding of positive charge could knock back a heavy alpha particle like that. It meant the plum pudding model, it was dead wrong. There had to be something incredibly small, incredibly dense, and positively charged hiding inside that atom. So, Rutherford's discovery just completely rewrote the book. The atom wasn't some dense pudding. Nope. Turns out it's mostly empty space. All that positive charge and pretty much all the mass was packed into this teeny tiny, super dense core he called the nucleus. And the electrons? He figured they must be orbiting this nucleus from way, way out. And this gave us this really cool picture, right? The planetary model. You've got electrons orbiting the nucleus just like planets orbiting the sun. It's a great image, but it had a fatal flaw. See, according to the physics they knew back then, an orbiting electron should be constantly losing energy. It should be radiating it away, spiraling closer and closer to the nucleus until, poof, the whole atom collapses. So why doesn't everything just instantly disappear? I mean, this was a massive crisis for physics, and a Danish physicist named Niels Bohr came up with a pretty radical idea to fix it. Bohr basically said, hey, maybe the old rules of physics just don't apply down here at the atomic level. He proposed that electrons can only exist in very specific, fixed orbits, which he called energy levels. Think of it like rungs on a ladder. An electron can be on one rung, or it can jump to another rung, but it can never just float around in the space between the rungs. And here's the beautiful proof. When an electron jumps down from a high rung to a low one, it spits out a little packet of light, and that light has a very specific color. This creates a unique barcode of light for every single element. It's like an atomic fingerprint. Scientists had been seeing these weird barcodes for years, but they had no idea what caused them. Bohr's model finally explained it. It was brilliant. Bohr's model was a giant leap for sure, but science never stops digging, right? And the final chapter in our story, well, this is where things get really weird, thanks to the bizarre rules of quantum mechanics. This right here is Heisenberg's uncertainty principle, and it just completely nuked the whole idea of neat little orbits. Think about it like this. To see where an electron is, you have to hit it with something, right? Like a photon, a particle of light. But the very act of hitting it with that photon knocks the electron off its path. So you can't know where it was going anymore. Just by looking at it, you change the outcome. It's wild. So what does this mean? It means we had to ditch the simple idea of an orbit and replace it with something much, much stranger, the orbital. And an orbital is not a path, not at all. It's a 3D cloud of probability. It doesn't tell you where the electron is, it only tells you where you're most likely to find it. We went from a tiny solar system to a fuzzy, uncertain cloud. And that's where our detective story ends. Not with a neat and tidy answer, but with this incredibly beautiful and profound mystery. The solid real world you see all around you, it's built on a foundation of these fuzzy probability clouds and fundamental uncertainty. So the case of the atom isn't just closed, it's blown our minds open to a universe that is so much stranger and so much more wonderful than we ever could have imagined.